So in this lecture, I will present the interaction between photons and atoms in a specific context of the cavity QED experiment we realized in Paris together with Serge Haroche and Jean-Michel Raymond. And then I will finish with some perspective of new way of controlling the interaction between Rydberg atoms in order to perform a quantum simulation. But before starting into the topic, I would like to introduce the lecture by this short text by Schrödinger that you may already have seen, and that I will read. Whenever experiments with just one electron, one atom, or one molecule, in thought experiment, we sometimes assume that we do. This invariably entails ridiculous consequence. So that sets the skin of the kind of work I will present today, which deals with describing experiment where one effectively deals with single atoms, single photons, single quantum objects. And it's amazing to see that for the founding fathers of quantum theory, who understood very well their theory, all a part of theory was considered as inaccessible. And the strange thing of quantum theory, so we'll tell more about the strangeness of quantum theory later, were kind of rejected in a world where you can never test it with experiment. And my goal today is to present you experiment, today and the other lecture, to present you experiment in which, indeed, one can do this kind of experiment with just one quantum particle. And more, in this experiment, we even observe the ridiculous consequences of quantum theory, which means that the founding fathers of quantum theory were very strong, we already know that, and they already understood very deeply all the formalism, even if they sometimes refuse to accept the consequences. Indeed, these consequences are real, and to make them real, then you have to do the experiment. So I'll describe this kind of experiment. So, of course, there are many systems in which one manipulates single quantum objects. So I just depicted there a few of them. In quantum optics, there was huge development of the manipulation of entanglement with photons, very often based on the generation of twin photons in parametric oscillators. And photons showed to be very good carrier for quantum information, for example, for application to quantum communication and quantum cryptography. Another very interesting platform is a cold atom platform. Laser cooling technique allow now to have atom traps in optical lattices. And if you do it in the right way, you can even have lattices with exactly one atom per side, so-called Mott insulator. And then you can even image in this structure the atom one by one and look at the evolution of the system at the level of single particles. Then there are other interesting single controlled quantum system in the context of solid-state devices. So here is an example where people can fabricate what we call artificial atom. Yeah? So artificial atom is one electron trapped in a quantum dot. And if you place this quantum dot in some resonance structure, like this pillar-shaped cavity, you realize you achieve a strong coupling in cavity QED and can manipulate the photons with the atoms in a very nice way. Cavity QED is also very well developed with real atom inside cavities and in different contexts. Sometimes people consider optical cavities and the way to manipulate optical photons in optical cavities. In my case, I will consider more the interaction of Rydberg atom with microwave photons, but most of the concepts also apply to optical cavity QED. Ion traps are also another very well controlled system where the vibrational mode of trapped ions plays a role of the field, resonant field mode of the cavity. And let me finish by mentioning a field which is very, very close now to what we performed with the Rydberg atom in superconducting cavities. It's the so-called mesoscopic circuit physics, or the circuit QED field, in which the artificial atom is a small superconducting circuit made of a combination of Josephson-Johnsons, capacitors, inductances, coupled to a microwave resonator, which is itself fabricated on the chip. It's so-called strip-line cavity. It's a conductor which is broken at the end, where the microwave bounces back and forth, and where the quality factor of the resonance is so high that the strong coupling regime is achieved in a very similar way as I will discuss in the case of the Rydberg atoms. So, as I just told you, I will focus on the context of the cavity QED experiment we realized at École Normale Supérieure at Laboratoire Kastler-Brotzel together with Serge Haroche. And of course, I would like to mention here and to emphasize here the similarity between this experiment performed with single trapped photon in a cavity whose state is investigated by looking at interaction with matter and using matter to investigate the properties of light. With respect to the ion trap experiment I already mentioned, in which indeed you kind of exchange the role of matter and of light. In the case of trapped ions, the ions are trapped and the light is used in order to investigate the quantum state of the ions, not only the internal state, but the interplay between the internal state of the ion and the vibrational mode of the trapped system. And just to emphasize one of the similarities between the two systems, I just represented here two signals which demonstrate the quantum jumps of the system, which are a very clear way to emphasize one of the most important properties of the system I mentioned in the introduction with the Schrödinger sentence. In both systems, one can follow a microscopic system, here a single ion, here a few photons stored in a microwave cavity. One can follow the evolution of the system as a function of time, basically in real time, and one can investigate the quantum properties of a single quantum particle in a single realization of the experiment. And these trajectories in a single realization of the experiment are very nice demonstration of a quantum feature in which, indeed, the founding fathers of quantum theory were not believing the fact that there exists quantum jump. In the quantum formalism, if you apply property, measurement, projective measurement leads to quantum jumps, abrupt jumps of the quantum state. So some of the physicists realizing that were not believing that one never could observe them. Indeed, they were observed both in the ion system and in the cavity QED system. So more precisely, what is the Rydberg atom cavity QED system? So it basically consists in a high Q superconducting cavity, which behaves as a very good trap for microwave photon, in which a beam of Rydberg atom is used in order to extract information about the field after interaction. And in the first lecture, in the first lecture of this talk, I will describe the resonant and the non-resonant interaction between Rydberg atom and cavities, and I will show you how you can use this system in order to explore some fundamental feature of quantum theory of measurement, and in particular, some of the most counterintuitive aspects of this theory. And so I will present quantum demolition, photon counting, and Schrödinger cat state preparation and observation of their decoherence. So in the last lecture, I will switch to another more recent application of Rydberg atom, which consists in using this very well-controlled system as a way to perform quantum simulation of other systems like solid-state devices. And I will present a project and present the feature of Rydberg atom for this field of quantum simulation. So as indeed, I have 5 lectures, so I would like to emphasize that we have time, so I'll try not to rush too much. And do not hesitate just to interrupt me at any time, ask questions. It should be kind of interactive lecture. So as introduction to the field, I will start with some brief historical introduction. So what is the beginning of cavity QED? It can be probably traced back to the late 80s, where already physicists were considering, like Maxwell, Hertz, and later Sommerfeld, they were considering the effect of boundary condition on dipole radiation. So it was more in the background of radio wave, of radio frequency radiation. And it's amazing to see that this problem was already considered by Sommerfeld in the context not of the dipole of a single atom emitting close to the surface, but in the context of the emission of radiation by a big antenna, which is modeled by a dipole, which radiates just over the Earth, which is considered as a conducting surface for radio frequency. And indeed, even if the two systems are very different, one is macroscopic, the single atom is microscopic, many concepts are common to this and common to the quantum and classical model. Then, later in the 30s, London, Lennard Jones studied the atom-metal surface interaction. So the interaction which occurs when atoms are put close to a surface. And then I would like to emphasize a bit more this paper, 1946, which is kind of one of the foundations of cavity QED, which is the description of the coupling between single spin with a resonator at resonance with a flipping transition of the stream as introduced by Purcell. And I think it's very instructive to go back to the original paper where this effect of spontaneous emission acceleration due to the resonator was investigated. So this is a very interesting thing. You can find this paper. You have to look a little bit in the literature to find it because it's indeed a short note in the proceedings of the American Physical Society in 1946. And if you just go to the Physical Review website, you don't find it because it's abstract of a conference, so it's not referenced on the Physical Review website. So you find it through Web of Science, for example. And then in this issue of Physical Review, you have the proceedings of this conference. And it's amazing to see that in a few lines, there is everything about this paper about the Purcell factor, describing the enhancement of radiation of a dipole coupled to a resonator. And in this case, all the argument is developed here. Purcell starts by describing the lifetime of a spin just in free space, which is like a huge number, 5 × 10⁻21 seconds. And then he explains an argument in a few lines in which basically he proposed to, he explains that if the emitter is placed into the cavity, this number, which is the number of radiation oscillator per unit volume and per unit frequency range, have to be changed due to the presence of the cavity to a very simple number, nu over q, which is one mode, indeed, 1 over nu over q, which is represents the density of mode in a cavity, where basically you have one mode in the width of the resonance. And then this mode, the unit of your volume, becomes the real volume, the actual volume of the cavity. And just by rescaling the usual spontaneous emission rate by this argument, he finds some enhancement factor of emission of photons in a cavity, which is proportional to the quality factor of the cavity, so better cavity are better for this effect, and inversely proportional to the volume of the cavity. If photons are more confined, you have stronger interaction between single atoms and single photons. And then he puts the numbers, and the impressive thing is that you win something like 14 orders of magnitude with realistic numbers in the case of the spin coupled to a resonance circuit. So you see that at that time, physicists were able to explain all the physics in a very short and very compact paper, and I think the present trend is kind of not going in that direction. So let me come back to the next step of the cavity QED history. So after this founding Purcell paper, there is a very important work in 1947 where Casimir introduced the so-called Casimir effect, basically which consists in considering the control and the modification of vacuum fluctuation when you put the atom between two mirrors, and basically this is related to the effect of suppression of some radiation mode on the frequency on the resonant frequency of the atom, which could be considered as kind of universal things, but which are not. The frequency of transition of atoms depends on field boundary conditions around the atom. Then, a bit later, Schwinger made some considerations about the boundary effects, so conducting surfaces close to emitter in the context of synchrotron radiation. So you see the widespread of fields investigated there from radio frequency to synchrotron radiation. Then, in the late 50s and 60s, masers and laser physics started, and then not a single emitter was considered, but the collective radiation of atoms in cavities was the basic of the concept of maser and laser, as initially studied by Tones, Shallows, and many other physicists. Then, for going back to single emitter or microscopic emitter, there was a seminal experiment in 1974 by Drexhaig, who observed modification of the fluorescence of molecules when they are placed close to surfaces. So that was the first experiment at the level not of atoms but molecules. And then in the 80s, a lot of technical development occurred. Use of lasers in the labs for many experiments become very routine things. And then a first experiment was performed at the NS, at École Normale Supérieure, in the group of Serge Haroche, demonstrating the acceleration of spontaneous emission of a single Rydberg atom in a cavity. Then similar experiments, either suppressing or enhancing spontaneous emission, were performed in MIT in the group of Dan Kleppner, in Seattle, in Yale, Rome, and many other places. So let me just focus on the first experiment, which was performed at École Normale in the group of Serge Haroche. This was performed before I joined the group. And you can see here the signal observed at that time. So it was an experiment in which they observed in 1983 the enhancement of spontaneous emission of a Rydberg atom. Indeed, it was a small sample of Rydberg atom placed in a superconducting Fabry-Perot cavity. So at that time, the quality factor was 10 to the 6th. So I will tell you more about this kind of quality factor. The frequency of transition was hundreds of gigahertz, and the observed acceleration rate of spontaneous emission was a factor more than 500. So it's not just a marginal effect, it's a huge effect. And it was the first experimental evidence of a Purcell effect, the fact that single emitters, two-level emitters in a cavity have spontaneous emission rate which can be accelerated. So here is the signal monitored in the experiment. So the Rydberg atoms were detected by ionizing them in some electric field. So you have the atom prepared, you increase the electric field, and at some threshold, you ionize the 33S level, which was initially prepared by lasers, and then a bit later, you ionize the level to which the atom can spontaneously decay, the 22P Rydberg level. And then you can compare the ionization signal with and without cavities as a function of number of atoms in the cavity. And basically, this line corresponds to the atoms essentially in the S state, because at the time scale of the experiment, where the cavity is non-resonant, you mainly have S state atoms. And then the peak showing up on that side is a transfer to the P level due to the cavity put at resonance. And you see that cavity have a very strong effect on this spontaneous emission. And I like very much this graph, which is extracted from the paper, the original publication, because here you have manual annotation by Jean-Michel Raymond, specifying the average atom number. These experiments were not performed with single atom, with controlled number of atoms. It was small number of atoms with Poisson statistics, but still the effect is clearly demonstrated. So later there were other experiments demonstrating not acceleration, enhancement of spontaneous emission, but suppression. And suppression was demonstrated by Gabriel C. and Demelt at Seattle when they did this very famous experiment where they trapped a single electron for a huge amount of time and made the most precise measurement ever of the gyromagnetic factor of the electron. And the trapped electron, it was in some conducting structure, the trapping electrodes, and these electrodes play a role in the flipping rate of the spin in the experiment, and indeed the experiment was arranged in such a way that they observed inhibition of spontaneous emission. Back to the context of Rydberg atom, in the same year, Hewlett, Hilfer, and Kleppner observed suppression of spontaneous emission by putting a Rydberg atom between two parallel plates, arranged in such a way that the distance between the two plates is smaller than half the wavelength of the emitted radiation. And they suppress the radiation mode for spontaneous emission, so they suppress spontaneous emission. Indeed, this pioneering experiment was already performed with circular Rydberg atoms that I will present and discuss in more details in this lecture. So the conclusion is that spontaneous emission that one could consider as given by nature for a given atom is not indeed, and depends on the density of mode of the electromagnetic field, which have some value in vacuum, but which can be modified if you put conducting surface around the atoms. And most of the work I will present now is based on this effect of control of interaction between field, microwave field, and single Rydberg atom by controlling the structure of the electromagnetic with mirrors and with cavities. So let me finish with the history. Up to now, I just described effects that I would qualify as perturbative effects. In perturbative regime, where basically the cavity factor was kind of low, so I will be more specific about this later in the lecture. But basically, when the low cavity factor, you perturb the usual evolution of the atom. So for example, the exponential decay one observed in spontaneous emission. But you can even do more if you do it to the non-perturbative regime, where the coupling strength will become larger than the dissipation rate. And indeed, that's the physics of this kind of physics where the strong coupling regime is achieved, started basically in the middle of the 80s by the so-called Rydberg atom micromaser experiment, which were performed both at École Normale in Paris and in Munich in the group of Herbert Walter. And I would like just to mention here the first micromaser experiment realized in the Walter group by Dieter Meschede in Munich, where indeed they realized a very specific maser called the micromaser, where some microwave radiation accumulates in a cavity in a regime where at a given time there is only one emitter in the cavity. So at a given time there is either 0 or 1 atom active in the cavity, but the quality factor is so good that even if the atom leaves the cavity, the field is still there at the time the next atom enters. So that's the micromaser regime. So the experiment is depicted here, and you will see again the basic elements of Rydberg atom cavity QED experiment. An atomic beam, which is vertical here, enters a cryogenic environment in order to have a good superconducting cavity and a good control of blackbody radiation. Rydberg atoms are very sensitive to blackbody radiation, and you have to protect them from blackbody radiation to have well-controlled cavity QED experiment. So the superconducting cavity is there. It was a cylinder-shaped cavity. The atoms are sent through the axis of the cylinder, and they enter into two small holes, which are also used as a waveguide below cutoff to inject a microwave eventually in the cavity. Then some laser beam excites the atom just before entering the cavity. So that's rubidium atoms, and here you see this atomic signal as a function of the frequency of the cavity, which can be tuned either with this big screw or with piezo stack, which is on the other side. So when you scan the cavity frequency over the 53P to 51D transition of rubidium, you see this peak, a decrease of the population of the 63P, corresponding to emission of photons in the cavity mode. And this is the non-perturbative regime. This is a regime where once a photon is emitted in the cavity, if interaction time is long enough, the evolution is not just exponential decay of the atomic energy, but the atom can periodically emit and reabsorb the photons in the so-called Rabi, vacuum Rabi oscillation phenomena that I will present in more details later, but I would like very much to mention this seminal experiment about microwave maser, which was demonstrating and entering the strong coupling regime in which the vacuum Rabi oscillation basically becomes faster than the decay of the field energy in the cavity. So I just resume there the two important regimes of cavity QED. So weak coupling regime, in which the atom field coupling is small as compared to dissipation strengths, where basically qualitatively the evolution of the system, the light matter system, remains marginally affected. The exponential decay of population remains exponential decay, but it's just faster or slower, depending on the parameter. Then the strong coupling regime, in which the atom cavity interaction is stronger than any dissipative process. And indeed, this realizes a very well-controlled fundamental quantum system that I would consider as the simplest non-trivial matter field coupling situation, where a single two-level quantum particle, an atom, is coupled to a single mode of the electromagnetic field behaving as harmonic oscillator. So this leads to radical modification of atomic properties, and for example, the most striking thing is that irreversible exponential decay is replaced by coherent exchange of energy, the so-called vacuum Rabi oscillation I already mentioned. And then it gives a lot of very efficient tools for manipulating the atom and the field, and to fabricate some entangled states of these systems, which are of very high importance in order to play with the most basic concepts of quantum theory, especially the quantum theory of measurement that we can investigate in very much details with this system. So going a little bit more in the techniques, I'll now mention the 4 timescales which are relevant in this kind of cavity QED experiment, and more generally in experiment where you investigate coupling between light and matter. So the atomic level lifetime is the first parameter characterizing dissipation. So I will name it here T hat, and gamma is the spontaneous emission rate of the atom. Then the second dissipative characteristic time is the photon lifetime in the cavity. It's the characteristic time of the exponential decay of some energy injected in the cavity. And it's important to realize that this decay time of energy does not depend on the kind of field you have in the cavity. In the cavity, when you have some electromagnetic field with some energy, either one photon or a lot of photons, it always decays at the same rate. The average energy decays at a rate 1/k. Then parameters characteristic of the interaction between the two-level systems, the atom and the cavity. So this parameter that I will name the vacuum Rabi frequency, it's a matrix element between the atom in the upper state and cavity empty. And atom in the lower state and cavity containing 1 photon. And the important time scale is here, what I call T-vac, is the period of vacuum Rabi oscillation. And then the atom-cavity interaction time, which can be very long if the atom is trapped, but in fact, with the Rydberg atoms, the atom is not trapped, so it has some finite interaction time with the cavity, limited by its velocity and the geometry of the cavity. And then the strong coupling condition reads like this. You need to have an interaction which is long enough so that you can see the effect of the coupling with vacuum, basically, which means that the product of the vacuum Rabi frequency times the interaction time have to be of the order of 1 or larger than 1. Then the Rabi oscillation period, the current evolution timescale, and the interaction time have to be short enough so that the damping time does not play a role and are longer time parameter, making dissipation negligible as a first approximation. And then, indeed, I can give orders of magnitude of these numbers, the coupling, the dissipation timescale, in different systems of cavity QED. I will not investigate all of them in my lecture, but indeed, it's good to have an idea of all the kind of parameters. So here are the 4 kind of different contexts in which cavity QED concept I'll present can be used. So optical cavity QED experiment, where you have very high Q optical mirror containing optical photons, and where atoms with optical transition interact with the field. So typically this experiment are performed in the group of Jeff Kimball in Caltech, in the group of Gerd Rempe in Munich, and now in many other groups. So typically, the coupling strength is of the order of tens of megahertz. The dissipation rate of the cavity is in the range of hundreds of kilohertz, which is very impressive. They can really fabricate very, very good optical mirrors. And then the dominant dissipative channel is the atomic decay, spontaneous emission on the resonance line of alkali atoms, whose line width is typically of the order of tens of megahertz. So you see it's already strong coupling, but not very deep in the strong coupling regime. Interaction time, if you have very slow atoms or even trapped atoms in the cavity, as in the experience of Rempe, basically the interaction time is set by the trapping time of the atom, which can be as large as seconds or several seconds. So the other important field is solid-state cavity QED. I already mentioned the quantum dots in some pillar resonance structure. So typically here, the coupling is much, much stronger. And the reason for that is that these quantum dots are of large dipole, but that the main effect is the field confinement. Typically here, the cavity is made of 2 Bragg mirrors with the distance separating the mirror of the order of 1 or a few wavelengths. Whereas in optical cavity QED, the distance is typically hundreds of micrometers. So the cavity volume, it's huge as compared to that, and which explains the difference in the strength of coupling factor, which now goes in the range of tens of gigahertz. Indeed, these tens of gigahertz, the strong coupling, have to be moderated by the fact that dissipation is also much faster in the system. The cavity line width is typically of the order of 1 gigahertz, so huge as compared to the optical case. And the damping, the spontaneous emission, the decay rate of the quantum gates, the quantum dot is very fast, because in solid-state devices, matter is dense, there are a lot of interaction, and indeed the lifetime is in the range of nanoseconds. Of course, the system is trapped. It's just in solid-state matrix, and interaction time is virtually infinite. Then another very interesting solid-state device, which indeed knew a huge development in the last year and was performing now very beautiful experiment, is circuit QED, where the solid-state device is a superconducting circuit, I already mentioned. So the coupling strength is kind of intermediate, hundreds of megahertz. Dissipation is much weaker than in quantum dots, in the range of hundreds of kilohertz. Interaction time is very long, and the factor of merit of this system is very good. It's comparable to the factor of merit of microwave cavity QED I will discuss now. So microwave cavity QED is dealing with Rydberg atoms and superconducting cavities. Typical coupling strengths are in the range of tens of kilohertz, so that the weakest coupling among all the systems. But the strength of the systems is also that dissipation is the weakest as compared to all the other by many orders of magnitude. So the decay rate of the photons in the very best cavities put the line width of the cavity in the range of 1 hertz, and the decay time is a fraction of a second for the cavity. And the lifetime of the atom, if you use specifically the circular Rydberg atom, is in the range of tens of milliseconds, which makes the atomic life width like 30 hertz, so a very small number as compared to the coupling. The interaction time, which is a strong limitation with respect to solid-state devices, was in the range of tens of microseconds and was recently pushed in the range of hundreds of microseconds by using slow Rydberg atoms. So I will tell you about this slow Rydberg atom experiment in the end of this first lecture. So let me now give a general outline of the lecture. So in lecture 1 to 4, I will focus with cavity QED with Rydberg atoms. Lecture 1 will be, the next part of lecture 1 will be devoted to the strong coupling regime and the resonant interaction between a single atom and a few photons stored in the cavity. Then in lecture 2 and 3, I will investigate quantum non-demolition photon counting, the realization of an ideal projective measurement of the photon number in the cavity. And then I will investigate some consequences and some manipulation of the field using this quantum non-demolition photon counting method. So we'll observe quantum jump, we use the method to perform quantum feedback, and we use it and we use some spatial analysis in order to follow a single quantum trajectory in the best way, putting all our knowledge of the experiment into the estimation of the quantum state of the field at a given time. So I will finish this part with a part about quantum state estimation. And then in the fourth lecture, last lecture about Rydberg atom cavity QED, I will investigate the interplay between quantum measurement and Schrödinger cat state and the decoherence problem. And in the last lecture, I will keep the Rydberg atoms, but drop the cavity and consider the interaction, the direct dipole-dipole interaction between the Rydberg atoms and the way to manipulate optically the state of the atom by trapping them in order to build a quantum simulator out of Rydberg, out of circular Rydberg atoms. So let me start with the outline of course 1, of lecture 1 now. So I will first introduce the theoretical, the formal background of this experiment, which is the so-called Jaynes-Cummings model. And then I will present the practical system we use in the experiment, which is made of Rydberg atom in the cavity. And I'll present vacuum Rabi oscillation, which are the signature of the strength, the strong coupling regime achieved in this experiment. And then I will present, if I have time today, if not, it will be for the second lecture today, the Rabi oscillation in a small coherent field injected in the cavity, which presents many fundamental quantum features, and which is one of the most efficient way in order to prepare so-called big Schrödinger cat states in the cavity. Big means something like a superposition of vacuum with 44 photons, which is not that big at the scale of macroscopic things, but which is already big at the scale of controlled quantum systems. So one atom, one mode, the Jaynes-Cummings model. So basically, the generic view of cavity QED experiment is the realization of a simple generic system make of a spin, and I will very often refer the atom as a spin. Of course, it's not a real spin. It's a fictitious spin, which is equivalent to any two-level system. And so I will assimilate the two-level atom with upper level E and lower G to a virtual spin in order to use the language you already know about spin, about magnetic resonance of spin, and things like this. Then the other part of the system is a spring to which you can imagine some mass hanged. Indeed, in the real cavity, we don't have a spring and a mass, but we have a single mode of the electromagnetic field, which, when you quantize the electromagnetic field, behave as a single harmonic oscillator. So with quantum states which are equidistant states, separated by some energy, which equals h nu, where nu is the frequency of the mode, so the states are separated by the energy of a photon. And then, in this model, we have to consider the coupling between the spin and the spring. In the case of Rydberg atom, it will be electric dipole coupling, and I will denote it by omega naught. Indeed, of course, I will discuss this in the context of Rydberg atoms and microwave photons, but any cavity QED experiments use the same formalism. Coupling may be different than dipole coupling. Physical systems may be different, but the physics will look the same. So let me tell a word about field quantization in a cavity as compared to field quantization in free space. So I don't know how much time I have to spend on this slide. Indeed, I would like to know who among you are familiar already with field quantization in free space. So a fraction of you, but not all of you. So my goal is not to provide a full course about field quantization, free field quantization, but I'll try to give you an idea of the way it proceeds. In the context of cavity, indeed, the method is formally exactly the same as compared to quantization in free space. So for quantizing the electromagnetic field, basically, you start from classical physics, and the first step consists in decomposing the classical electromagnetic field in so-called classical modes. And in the case of the resonator, it's especially clearly defined. The eigenmodes of the fields are the resonance of the cavity. So I think all of you are familiar with the Fabry-Perot cavity. It transmits light only at discrete frequency, which corresponds to the modes of the cavity. So if you are not in a cavity, but in free space, you have some freedom in defining the modes because there are not mirrors defining them. And usually you have to take a basis of the solution of the Maxwell equation, and the most common choice consists in using plane waves for expressing the electromagnetic field in free space. So in the case of a cavity, you have no freedom. You choose the resonant modes, the classical resonant modes of the cavity, and up to this point, you just do classical electromagnetism. And basically, a given mode have some expression of the electric field, classical electric field, as a function of position of time and time. It has some amplitude for a given frequency. For each frequency, for each mode, you will have some amplitude. And then there will be some geometric factor determining the shape of the mode, which is this function f of r. And the temporal evolution of eigenmodes of resonator, by definition, eigenmode is a single frequency mode. So it oscillates with a single frequency with this exponential term, e to the I omega t. So here, E is a real amplitude. F is a complex, most generally, it's a complex function because it can describe also the polarization of the field. If you have a cavity with a mode which is circularly polarized, you need some complex function to describe polarization as a function of position. And to make the field real, you add the complex conjugate. So that's the expression of the classical field of a given mode, a given monochromatic mode. And then the trick, once you have decomposed the classical field into modes, the trick to quantize is kind of automatic. Each mode becomes some harmonic oscillator. So I will not discuss the argument in details. I just give the recipe. And then the electric field, which is a real function here, become an operator. Indeed, I should have dropped time here. In the Schrödinger picture, this operator does not depend on time. And the expression is very similar to the classical expression, except the fact that you have to introduce creation and annihilation, photon creation and annihilation operator, A and A dagger, in place of the exponential factor as a function of time. And then you get an operator which does not depend on time, but which, when you take it as an average value on some state, the state depends on time, will give you some expression of the average electric field, which is very similar to the classical expression. So the fundamental relation is a commutation relation between operator A and A dagger. And as I told you, these operators represent the operator usually introduced for describing harmonic oscillator. So they respect the commutation relation of creation and destruction operators of excitation in harmonic oscillator, A dagger, commutator equals 1. So then specific important parameters show up in the context of cavity QED. Here is an important value. It's the normalization factor of the electric field operator. So this is not an operator. This is a number. It has the dimension of some electric field. Operators A and A dagger have no dimension. And we choose the function, the geometric function describing the mode as also dimensionless function. So here, the magnitude of the electric field corresponding to one photon in the mode is fixed by this number, E omega, which is the square root of the energy of one photon, h bar omega, divided by basically the volume of the cavity and the vacuum permittivity, which is there to make the dimension of the electric field correct. But the important term is the ratio between the energy of photon and the volume of the cavity. It means that this field, that I could also have called the vacuum field, is the field you get if you put the energy of one photon in the volume of the cavity. This has to do with the density of energy in the cavity. And so the smaller the cavity, the highest the single photon or the vacuum field in the cavity. And you see directly on this formula that by changing the volume of the cavity, you can change the magnitude of vacuum fluctuations, the vacuum of the amplitude of the field related to vacuum or to one photon in the cavity. Usually, when you are in free space, instead of the cavity volume here, you have a fictitious quantization volume. Because in free space, it's easier to quantize the field as if you was in the huge cubic cavity with dimension, with a spatial dimension of size big L. And instead, in vacuum, when you quantize, you have here L to the 3, L cube, which is the volume of the quantization box. And of course, in all calculations of physical quantities in vacuum, you have to make the size of the fictitious cavity go to infinity, and the size of this cavity have to eliminate in the end when you take the limit of infinite cavity in order to calculate quantities. So indeed, the situation is simpler in a cavity where you have a physical volume and you don't have to care about effects related to finite quantization volume and the complexity of the math related to that. Yes? So maybe, I don't know if this microphone works. Yes.
I want to ask you that, could you please explain the Fabry pericavity here again?
For different...
Fabry pericavity.
Yes.
Because you explained something that Fabry pericavity is... I didn't get the explanation about Fabry pericavity.
So Fabry pericavity is typically, all cavities are kind of Fabry pericavities. So they are made of usually two curved mirror, or one curved mirror and one planar mirror, which make the field confined under many reflections. If you have two flat mirrors, you may have some resonances, but the propagation between two planar mirrors may be unstable, and after a lot of zigzag, the light may escape, and it's not a very good cavity. So usually in the Fabry-Perot cavity, to have a good confinement of the field, you use curved mirror arranged in such a way that the photons does never touch the border, and then that's a way to get a high Q. And so I will not formalize it, but then when you solve the Maxwell equation to find the modes of the cavity between the mirrors, you have in approximation, in so-called paraxial approximation. So if you consider a field which is not too divergent, the spatial structure, so the function f of r in the cavity, correspond to a so-called Gaussian mode of the electromagnetic field. So if you want to figure out the shape of the function f we have in mind in case of Fabry-Perot cavity, the transverse profile is a Gaussian, and the amplitude of the electric field vary in the radial direction, like exponential minus R2 over some parameter, which is called the waist of the mode. And then, in the other direction, you have the interference between two counter-propagating beams. So you have nodes and antinodes, which are described by some cosine function, slightly modified by the fact that when the beam converges, the phase is slightly modified. So I cannot just present a lecture about these modes, but basically, if you send the right laser beam in the cavity, you can match these modes. And indeed, if you excite only one mode, you have to use this function f of r to describe the mode. And this results from the interference between all the reflection going back and forth between the mirrors.
Thank you.
Okay. And so in practice, the shape which will be useful to describe our experiment is the shape of a Gaussian mode with a transverse profile, which is given by Gaussian, and with a longitudinal profile, which is a stationary wave. And of course, to have strong coupling between atom and cavity, we need to put the atom at antinodes of the electromagnetic field so that they see the cavity mode. It's amazing to see, and it's kind of obvious. If you put the atom at a node, it does not see the amplitude of the field. So it's kind of decoupled from the cavity, even if it's inside. And that's the role of this function f of r to describe this effect. Other questions? So this is the most important quantity, the strength of the electric field related to a single photon put in the cavity. Then here you have the definition of the cavity volume, which is primarily the integral of the geometric function f. And indeed, one has some flexibility in the choice of normalization of this function, which is in principle arbitrary. And the common normalization is that the max of the modulus of this vector is normalized to 1, which means that this electric field is the electric field you have at the position where the field is maximum in the cavity mode. So here, f of r is maximum here at this position. And then with this definition of normalization, the cavity volume is more or less the geometric volume of the cavity, which is here the product of the transverse dimension, which is W naught, the waist, times the distance between the mirror. That's the cavity volume in this case. D is this distance. Okay? So this function can be complicated. If you have a spherical cavity, you can have many different functions, but the interesting one for us will be the Gaussian shape. So then quantization basically consists in putting these two operators characteristic of harmonic oscillators. And then that's it. You have all the formalism you need for describing the quantized electromagnetic field, and provided you already know about harmonic oscillator, you know about the quantum physics of the field stored in a high Q cavity. So here I would like to make a remark about the power of this quantization method. Indeed, it makes a classical, very complex problem very simple. What is the problem? The problem, if you would like to start from first principle, how to quantum mechanically describe the field in a volume limited by mirror. So from the fundamental point of view, if you want to make a microscopic model, you would have to treat the quantum interaction between the field, but not only the field, but also the atoms and the electrons which are in the mirror. And this would be a very, very complicated task. Describing quantum mechanically the interaction between light and the atoms of a mirror is a very complicated problem. But indeed, this formalism tells you that it's not necessary to solve this problem. You can keep this problem at the classical level, and here it manifests just as fixing boundary conditions for defining the eigenmodes of the electromagnetic field. But indeed, you have to keep in mind that when you quantize the mode of the electromagnetic field, you basically slightly also quantize the matter. You also quantize indirectly the motion of electrons in the mirror, which are used in order to reflect the photons. And here we are talking about quantization of electromagnetic field, but it's more accurate and more exact to think about quantization of a kind of hybrid system, which is the charge inside the mirror interacting with the electromagnetic field. So this can appear as a kind of formal remark for you, because basically here, in the case of this kind of Fabry-Perot cavity, most of the energy is in the motion of the field and not in the motion of the charge in the mirror. But if you have in mind a very important field of circuit QED, where people have superconducting circuit having resonant mode, then the mode is really electric mode of charges in wires coupled to electromagnetic field. So the volume of the mode is comparable to the size of the wire. And you really quantize, as a rule, a resonance of a composite system, which is electrons interacting with light. And indeed, the power of quantum formalism is that even if you have many, many electrons, many atoms for building the wires, the quantization is very simple. You identify classical modes. You don't care whether this mode is only radiation or only oscillation of matter. You have a mode, and you quantize it. And the formalism is already very, very powerful. But indirectly, you quantize matter when you quantize the field in the cavity. OK, so then in the following of the lecture, I will consider a single mode. So here, alpha was some index allowing one to count the various modes of Fabry-Perot cavity. So I will consider only one, the one which is closest to resonance to the atom. And if your cavity is small enough, the free spectral range, the spacing between two resonances of the cavity is so large that when you have one mode nearly resonant, you can neglect the non-resonant interaction with the other one. So that will be the simplest situation. So let us now, so maybe there are still questions about field quantization. I am aware that for those of you who never heard about field quantization, this may be kind of hard slide. But keep in mind what you know about harmonic oscillator, and this will be enough for the rest of the lecture. I will not need more than the properties of single harmonic oscillator. OK? So then, interaction with atoms. So let us consider an atom placed at the center of this Fabry-Perot cavity. And I will name the two levels, the upper one and the lower one, E and G, and the atomic frequency I will denote by this omega hat. So I consider a single one in the cavity. Of course, in practice, sometimes you have more. A single field mode with frequency omega C. And in case of Rydberg atom, the coupling is determined by electric dipole coupling, the product of the dipole matrix elements between these two states and the amplitude of the electric field in the cavity. So in the Jaynes-Cummings model, we write the Hamiltonian of the system, making the approximation that damping is negligible. And then damping can be introduced later by introducing a master equation for the field evolution. So here are the various terms of the atom field Hamiltonian. With first line, the atomic energy. So you ignore the field in this term, and it's just an Hamiltonian which is formally written so that the energy difference between E and G is omega hat. So here you recognize the projector over E, projector over G, and if you take the average value of this on state E, you find plus h bar omega hat over 2, and if you project it over G, so you take the average value in the state G, you have minus h bar omega hat over 2. So this choice amount to write the Hamiltonian in terms of projectors in the subspace considered here, with a choice of origin of energy which is just halfway between E and G. So that's a common choice to have symmetric expressions. Then the energy of the cavity mode. So as I told you, cavity mode is formally an harmonic oscillator whose frequency, which is the cavity frequency, and then for a harmonic oscillator, you know that the spectrum of the Hamiltonian is given by this expression, where A dagger A is an operator which is a photon number operator for harmonic oscillator. If you apply this to the nth eigenvalue of energy, you get the n, the number of photons in the harmonic oscillators. 1/2 corresponds to energy of vacuum. Average value of photon number in vacuum is 0, and still you have some energy. So you have to understand this 1/2 h bar omega c as some energy with respect to some reference. And the reference energy is a classical reference, which is 0 energy if the harmonic oscillator is at rest at the bottom of the potential. So with respect to this classical energy, you have this 1/2 of h bar omega c, which represents the fact that a quantum particle is never at rest at the bottom of potential. It always has fluctuations of position and momentum ruled by the Heisenberg uncertainty principle, which makes the fact that vacuum have some energy, 1/2 h bar omega c, which have physical consequences. It's not just a formal writing of energy scale. So that's the two Hamiltonian of separate system. And then the coupling, physically, electric dipole coupling as the usual form, minus D, which is the electric dipole operator between E and G, and E of R, which is the electric field operator presented on this slide without the time. So then it's very convenient to write the dipole operator formally as a function of not projectors, but I would say pseudo-projectors, which are elementary operator constructed by combining bra and ket E and G. And so here in factor you have a vector which is just a list of free numbers, the free component of the dipole matrix element. And indeed, in a two-level system like this, the dipole operator is purely non-diagonal. It allows one to write it in this way. It connects the state in G together with the state in E, and it has matrix element between E and G and E, but no diagonal matrix element of the dipole operator, which is related to the parity of the operator. So this is the three basic ingredients of the Hamiltonian. And then this is valid. So the approximation here is to keep only one mode. And it is valid, as I told you just before, provided the cavity frequency is close to a single atomic transition. Of course, real atoms have many transitions. Real cavity have many modes. But if you are in the Rydberg level, you can arrange the thing so that one transition is favored. It's the one which is very close to the resonance of the cavity. So it means that the detuning with respect to one mode have to be much smaller than the frequencies, the eigenfrequency of the system, and that's a good approximation for a Rydberg atom. Then the important thing to consider only one cavity mode is that the width of the mode is much smaller than the distance between consecutive modes. So it means that the detuning and the width of the mode have to be much smaller than the free spectral range of the cavity, so that you can already consider one mode. So then I will just develop the formalism in a very standard way by modifying the expression of the atom cavity coupling. So you see here you have the product of two operators, the atomic one and the field one with combination of A and A dagger. And when developing this combination, I can rewrite the coupling as a function of a number, a real number omega of R, and elementary operators. So here I choose the simple situation where, indeed here, the expression of the coupling is just deduced by a combination of numbers we already saw. Here is the dipole matrix element. Here is the spatial function of the mode. And here is the amplitude of vacuum electric field, or single photon electric field. And all this I combine by defining it, defining the coupling as omega naught times the modulus of the function of f of R, so that I have a real number for the coupling. Indeed, this coupling form is important. In the first part of the lecture, I will completely neglect the spatial variation of the field mode. We'll put it just when needed. So just consider a constant coupling first, and then we'll adapt the expression where we have a coupling which may vary as a function of position. So then, from this Hamiltonian, which have 4 terms, I will keep only 2. So why do I keep only 2? I do what is called in the literature the rotating wave approximation. And basically, I neglect the green term with respect to the red one. So why do I neglect them? I neglect them because within two-level approximation, they lead to transition between states which have very different energy. So let's look, for example, at this state. If you make it act on an atom in G, it changes the atomic state to E. So from the atomic point of view, this EG is an excitation operator of the atom. The A is a destruction operator of photon. So when you apply this term of the Hamiltonian to the state, let's say, so G n, the state where the atom is the lower state, the field contains n photons. So the operation of A times E G, so this is 1, and this will be finally E. And if you make this operator act to n photons, how is the action of destruction of operator over n photon state? So it goes to n minus 1 state, because it's definition of destruction. And the important thing is the normalization factor that you have to remind, which is square root n. And so here you see that you have a state with n minus 1 photon and an excited atom. And if the cavity is close to resonance, which choose, then these two states are very close in energy. Here the excitation is the atom, and here you have one more photon as compared to here. So here you have a coupling between two levels whose energy difference indeed is the detuning delta between the atomic frequency and the cavity frequency. So this is small. On the other hand, if you consider the green terms, like A, G, E, okay, so over G, N, so I consider the last term, A dagger times E times G. So GG gives 1 again. So this leads to atomic state E. But now A dagger creates a photon. So there is one more excitation and a normalization factor here, which is indeed always in all these expressions, the normalization factor is always the larger of the two numbers there. So here it's square root of n plus 1. And you see that the energy difference, big delta between these two states, is like one more excitation in the atom and one more excitation in the field. So the detuning, this operator links two states which differ in energy by h bar omega hat plus omega c, which is a large number as compared to the coupling. So this term would lead to non-resonant coupling, and I will neglect them in the Jaynes-Cummings Hamiltonian. So basically, we go from the first line, which have all the terms, to the second line, where I only keep the red one by neglecting non-resonant coupling, coupling to states with very different energy, which is much weaker than nearly resonant coupling terms. And that's this Hamiltonian, which is the Jaynes-Cummings Hamiltonian. So then the important definition is here, the vacuum Rabi frequency, omega naught. And as I told you, I will consider a situation where the atom is placed now at the center of the cavity, where this modulus of R is unity. So let us look at the energy spectrum of the coupled system, atom plus cavity states. So on the left side of this, I have put the eigenstates in the absence of coupling. So if the dipole coupling is 0, and if the cavity is resonant, so we start with the simplest situation where we have exact resonance between the atom and the cavity, you see that the ground state is the state where both atom and cavity are unexcited, so that's vacuum and lower state of the atom. And then if you put one excitation, either in the atom or in the field, you climb up the scale of excited state by one photon energy, h bar omega c, which is also the atomic excitation energy. And as we have the resonant condition, these two states are degenerate. They have the same energy. Then if we go further by adding more and more photon, you see that resonant condition ensures that always you have a pair of levels which are degenerate. More precisely, the state G with n plus 1 photon, already considered before, is degenerate with the state, atom dopper state with n photon in the cavity. And then on the second column, there is the energy in the presence of a coupling. So I switch on the coupling. And the important point is that the Hamiltonian here does not have matrix element between different multiplicities. So basically, solving the Jaynes-Cummings Hamiltonian amounts to solve a 2 by 2 matrix coupling the two levels which are degenerate in energy. So that's very simple calculation to get the eigenvectors and the eigenenergy in the presence of the electric dipole coupling. Under the Jaynes-Cummings approximation, you just have a splitting of the levels, and the new levels are a combination of the old ones, and at resonance, it's just symmetric and anti-symmetric linear combinations of the level En and Gn plus 1. So we get new eigenstates, which are called the dress states of the atom cavity system. So it's composite system, and the usual notation for them is +1, plus minus n for designating the two dress states of the multiplicity corresponding to excited atom and n photon in the cavity. So the eigenenergy are written here. The black term is just the offset with respect to the origin of energy. And then the important term is the splitting of energy, whose magnitude is given by the vacuum Rabi frequency times h bar to get an energy times square root of n plus 1, where n is this photon number. And you see that even if the atom is excited in vacuum, you have a splitting. So that's a so-called vacuum Rabi splitting. And that's why omega 0 is named the vacuum Rabi frequency. So that's a very simple thing. And the only thing you have to keep in mind is that all this physics is the physics of many independent coupled pairs of levels. And it's never more complicated than that. So another important point, if you consider these states, is that the system is really quantum mechanically composite. The atom field state here is entangled. It is non-separable. You cannot factor it in the state of the atom times the state of the field. which means that even if it's just simple two-level physics, there is already entanglement there. So the last important remark is about the scaling of the splitting as a function of excitation, as a function of photon number. And the scaling is given by the scaling of the electric field in the electric dipole coupling as a function of photon number. And as the square of the electric field scales like energy is proportional to photon number, then the field amplitude is square root of photon number. And then you have to remember that it's not just n, but n plus 1, which is definition of the photon number. So that's all. That's all we need to describe the resonant interaction of a single two-level atom in a resonant mode of a cavity. So let's go to the numbers characteristic of the experiment. And let us consider now the dynamic of the system. So let us assume that we start with the atom in the excited state with the cavity in vacuum. What is the evolution? So you can calculate easily the evolution from the usual recipe of quantum mechanics. You have to decompose the initial state E0 into the eigenvectors of the coupled Hamiltonian. And it's very easy. You just sum the two eigenvectors and divide it by square root of 2, and you have the initial state as a function of the eigenvector of the Hamiltonian. Then you make each of these eigenvectors evolve as a function of time according to their respective energy. And you can easily show, and I suggest if you have not yet done this calculation to do it as exercise, if you start with vacuum and an excited atom, as a function of time, you expect some Rabi oscillation of the atomic and field population between energy completely contained in the atom, as it was the case for the initial state, to energy completely contained in the field. And the evolution is a coherent Rabi oscillation between these two states. So if you put numbers with Rydberg atom in cavities, the dipole is large. We'll see more details number later. The field amplitude is large because it is confined in a small volume. And then the strength of the coupling is like 50 kilohertz, corresponding to a vacuum Rabi period, a Rabi oscillation period on 20 microseconds. So 20 microseconds looks short. It's comparable to the interaction time of thermal atoms crossing the cavity, which are kind of fast atoms. These atoms are velocity typically 200-300 meters per second. And so you see that the coupling strength is good enough so that you can observe its effect with very fast atoms. So one expects this coherent Rabi oscillation, and now I will finish this first lecture by just describing experiments where we observe this vacuum Rabi oscillation. Yes?
Here you show the dynamics like the rest state basis.
Yes?
As soon as you're working, you should be in the rest state basis.
So I can write the state in any basis. It's my choice. So if I write it in the rest state basis, I have two components. Each one has some evolution with exponential minus e times its energy divided by t divided by h bar. But I can go back in the initial basis. So I can write plus and minus as a function. I can replace plus and minus by their expression as a function of e and g, and write the state in the basis I want. So it's an eigenbasis, but so then it's just mathematics. You have some initial state. You write this in the basis which is convenient to apply the postulate for evolution of the Schrödinger equation, and the good basis to write the evolution is the coupled basis because you know the eigenenergy. And once you are there, you have a vector which depends on time. You can choose to write it either in one basis or the other, just mathematics. And the nice expression to have an idea of the physics of time evolution is to come back to these states, which are the one you measure. Because in the end, we measure atomic energy. So to get the probability to detect the atom either in E or G, we need this expression. OK? Other questions about this expression? Yeah?
Now we are considering only one mode of
I am considering?
one mode of energy.
Yes, one mode of
interacting
the field.
with atoms.
Mm-hmm. Yeah. So other questions at this level? So then I switched to the experimental observation of this vacuum Rabi oscillation thing, which is simple to describe theoretically. Basically, it's two-level system coupling. But experimentally, in real world, with real atom, one have to fight slightly in order to realize it. And the reason one have to find is the fact that you have to isolate very much the field from the outside world and the atoms from the outside world. And so you have to trap the atoms in a very good photon box, which is made of two superconducting mirrors, which are nearly spherical mirrors. And indeed, there's photons, so these mirrors will confine the field and reflect it many times over the atom to make them interact with the field. So here I present you also a resume of the evolution of the technical quality of the cavity as a function of time, which was really an important challenge for the development of the Rydberg atom experiment I am presently describing. So the story started, the first superconducting cavity we had in this setup, interesting with circular Rydberg atoms, we got in 1994. And you see that it was not good enough to be in the strong coupling regime. The strong coupling regime corresponds to this line, where the vacuum Rabi frequency period, 20 microseconds, is 20 microseconds. And indeed, the lifetime of the first photons in our cavity was like 1/10 of the Rabi oscillation period. So we had to fight to improve the quality of the mirror. And we got this here in 1996. Basically, this damping time is maybe more demonstrative if you phrase it in terms of quality factor. So the quality factor we have for the mode here is 2×10⁸, which means that when you excite the field, it oscillates 2×10⁸ times before you lose the photons. So it's huge quality factor as compared to any other oscillating system, and it's what's needed in order to reach the strong coupling regime. So here with this cavity, and I will discuss the experiment realized with this cavity in the strong coupling regime, the photon lifetime was in a range of 200 microseconds, whereas the Rabi oscillation period, the expected Rabi oscillation period, is like 20 microseconds. So it's clearly the strong coupling regime. So as a function of time, you see that we improved a lot the quality factor by like a factor 10⁵, but I will tell more about this later. So the other important object is the Rydberg atom. So why Rydberg atoms and why circular Rydberg atoms? So Rydberg atoms have resonance transition between neighboring level in the range of microwave, which is well adapted with the kind of cavities I have in mind. The cavity with such a huge quality factor can only be realized if you use superconducting mirrors. And superconducting mirrors are not good mirror in optics. They are good mirror up to like 100 gigahertz frequency. Above this, the frequency of microwave is too close to the gap of the superconductor, and you can break the Cooper pairs with the photons, and the quality factor drops very fast with frequency. So we need spin, we need atoms with resonance frequency in the range maximum hundreds of gigahertz, and Rydberg atoms are good for that. If you choose principal quantum number like 50 and 51, the frequency of the transition is 51 gigahertz. So that's one first point. You have to match the frequency of the atom with the very good cavities that you can fabricate with superconducting mirror. The second point is that you want a strong coupling, and it appears that Rydberg atoms are very good for that because it's kind of geometrical effect. The Rydberg atom is a big atom whose size is the atomic hydrogen radius times the square of the principal quantum number. So, and if you put the numbers, the electric dipole matrix element on this Rydberg transition is like 1,500 atomic units. So it's a much bigger atom, which is kind of big antenna strongly coupled to the microwave field. Then the reason for which we use not ordinary Rydberg atom, but circular Rydberg atom is the lifetime. So what is the definition of circular Rydberg atom? It's circular Rydberg atom whose state corresponds to orbital and magnetic quantum number equal to the maximum value n minus 1. In terms of wave function, the wave function is a torus located around a circle, which looks very like the naive model of the Bohr atom, with one electron orbiting on a circular orbit. Of course, the electron is not like a planet orbiting around the sun. It's a wave. It has to be described by the Schrödinger equation. But you can figure out the circular Rydberg atom as an electron wave, which is curved around a circle with an exact number of wave oscillation around a circle. And this resonant condition can be seen as a way to enforce the quantization of the energy level of the Rydberg atoms. So basically, we consider two circular Rydberg levels with principal quantum number 51 and 50. So why circular? It's not just because it's very nice and simple atomic system. It's because the spontaneous emission rate in free space is much longer for circular Rydberg atom as compared to low angular momentum Rydberg atoms. So if you consider low angular momentum Rydberg atoms, they basically decay mainly by optical transition to deep level of the atom. And the emission at optical transition is typically in the range of hundreds of microseconds. If you go to the circular atom, I will give more detail later, but basically this level 51, due to electric dipole selection rule, have only one decay channel. It only decays to the next circular level, because all the other levels have delta M and delta L larger than 2, and it's not coupled by electric dipole. It means that instead of emitting optical photons, circular atoms only emit microwave photons. And if you remember the expression of the spontaneous emission rate, the spontaneous emission rate is proportional to the cube of the frequency of the transition. So you have a huge factor between optical transition and microwave transition, and that's why the lifetime of the circular atom is much longer as compared to the lifetime of ordinary atom. So that's why it's very interesting to manipulate circular atoms in the experiment, to have a lifetime in the range of tenths of milliseconds, which is like 3 orders of magnitude longer than the vacuum Rabi oscillation period I mentioned, which is 20 microseconds. So this will lead to complications, because technically preparing circular atoms is kind of challenging, but it's really worth due to this number. So let me tell you a little bit more about the circular atoms and the two-level approximation, which is non-trivial. So I don't want to go into the details at this level. I will tell more details about the atomic structure in the last lecture about quantum simulation. But basically, you have to be aware that there are a lot of levels in the Rydberg multiplicity, a lot of degeneracy. Basically, if you consider for given principal quantum number all possible value of L and M, you have like n square level. And n square is like 2,500 in our case. So you have a huge number of levels in both multiplicity, like 5,000 levels there. And you may be amazed by the fact that I pretend that we just use a two-level transition. And the trick to isolate a two-level transition in a Rydberg multiplicity consists in applying some electric field on the atom. And the electric field lifts partially the degeneracy. So in presence of electric field, the magnetic quantum number M is still a good quantum number. So you can sort the level as a function of magnetic quantum number. And then you have a linear Stark effect. All the transition between all neighboring states is the same. It's the so-called Stark frequency. So the structure is simple, and provided you put the cavity close to resonance here, you have a very good two-level system. It's very good. It's not perfect, because you have a coupling from 51 to 50 circular states here. You also have a wrong coupling to another third level here. But this one is very, very small due to Clebsch-Gordon coefficient. So I will neglect this coupling, and I will consider that the circular Rydberg atom really relies neitherly isolated two-level system, provided the detuning between atom and cavity is small as compared to the stark splitting between the levels there. And indeed, the order of magnitude is that the stark frequency here is 100 megahertz, or several hundreds of megahertz, which makes it easy to have the atomic frequency close to a cavity resonance with a detuning of less than tenths of kilohertz. You can really only consider this transition in the description of the interaction. So I was maybe a bit slow as compared to what I expected. So I will just tell you the details in the next lecture, but just finish by showing you the Rabi oscillation signal we monitored in the experiment by monitoring as a function of interaction time, which in this experiment was varied by varying the atomic velocity. You see that when you start with an excited atom and the cavity in vacuum, we observed at that time periodic Rabi oscillations corresponding to coherent exchange of energy between the atom and the cavity. And you see that due to the presence of the mirror, once the photon is emitted in the cavity, and here it is emitted, the cavity contains one photon and the atom is now in the lower state, the field can be reabsorbed and re-emitted several times. And that's the signature of the strong coupling regime in this cavity QED experiment. If we were not in the strong coupling regime, we would observe spontaneous decay, exponential decay from E to J, and irreversible processes. And here, the signature of the strong coupling and the coherence of the system is this Rabi oscillation signal. So I will finish this lecture, this first lecture at this point. And in the next lecture, I will give you further details about the experimental system. And I will just, as an appetizer, show you that we can now do much better with a slow atom experiment. But that will be for this afternoon. Thank you, and maybe there are questions. For this lecture.
How does the atomic velocity is related with the interaction time? What do you
So the atomic velocity is related to the interaction time. So indeed, in the experiment, the interaction time is defined as kind of effective interaction time. And you can imagine that fast atoms interact shorter time than slow atoms. And so the point is that for defining the interaction time, we have to take into account the Gaussian shape of the beam. But basically, it's easy to define some effective interaction time because it corresponds to the fact that when the atom crosses the cavity, the splitting is just changing as a function of time, but you can integrate it because the eigenvectors does not vary as a function of time. So the Rabi oscillation angle is an integral of the Rabi oscillation frequency as a function of time, and this is proportional to the inverse velocity of the atom. So indeed, controlling the interaction time does not only rely on control of velocity, because you don't have infinitely fast atoms to get zero interaction time, but there is a switch in the experiment which can be used to change the interaction time. It is the Stark effect. So if you change the electric field applied between the two mirrors, you just change the atomic frequency, and the Stark effect of the circular transition is large enough so that you can put the atom on resonance or out of resonance by switching electric field. So the shortest interaction time are just realized by waiting that the atom is at the center of the cavity, and for a short time put it at resonance with the electric field. And that's the way to vary the interaction time. Yeah?
After the atom is in the cavity, how do you measure in which state it is?
Okay, so maybe I skipped this because we were running out of time, so I will tell about detection in the next lecture. Yeah?
About preparation of the Rydberg state, I don't know if you're going to speak something about it.
About the preparation.
Yeah. One thing that I always wondered about Rydberg state is that it is really close to ionization, right?
Yes.
So is it hard to prepare the Rydberg state?
So it's kind of hard to prepare, not hard once you know how to do it, but in the beginning it's kind of complicated. It's hard not because it's close to ionization limit, because it's still far away. So if I don't know if there is a chairman, but if the chairman gives me a few minutes, I can explain this. So I explain the detection first. To detect the atom, you apply some static electric field to ionize them. And you need like 100 volts per centimeter to ionize the atom. So you don't have electric field that big in the experiment. So the Rydberg atoms are close to ionization, but they don't ionize spontaneously. And here, when we detect them, we vary some electric field in the capacitor, and we use the fact that the ionization threshold depends on the binding energy of the atom. So the larger the binding energy, the higher the ionization field is. So when you ionize circular level, you first ionize 52 circular, then 51 circular, then 50 circular. And so you can selectively detect this and that and reconstruct the population of the various levels by resuming the measurement a lot of time. And then about one word about preparation of circular atom, but I can go much more in the detail if you want, either after the lecture or in another lecture. So basically, the difficulty is that you need to inject a lot of angular momentum in the atom, but you cannot do this directly with lasers because you have 1 unit of angular momentum per optical photon. Here we use a 3-photon excitation, and for some reason, a good level for starting the circularization is the F level of rubidium with principal quantum number m equal 2. And then to go to circular, I just mentioned the ingredients, and I can give you more details. You need basically to apply to the atom all kind of field you find in some atomic physics lab. So you have the laser light to inject energy into the atom to promote it in Rydberg levels. Then you have electric field to open the Stark multiplicity to lift the degeneracy between circular state and the optical level with Euler value of m. Then you need some radio frequency field perpendicular to the electric field, which ideally should be sigma plus polarized in order to induce transition from m equal 2 to circular state. And this radio frequency injects a smaller amount of energy as compared to laser, but a lot of amount of angular momentum, because radio frequency photons have 1 unit of angular momentum per photon. So you perform like a 50 photon transition here to prepare the circular atom. So you do this adiabatically, so that it's efficient, and you do this in the presence of a magnetic field to avoid the bad red transition, which are sigma minus transition, which are in principle degenerate. So if you don't apply magnetic field, you just populate all the levels by zigzag transition. So to avoid the zigzag, the magnetic field breaks the symmetry between sigma plus and sigma minus, and basically put sigma minus out of resonance. And that's the way to circularize the atoms. And then once you are there are not 99% pure, they are like 80% pure, and you have some purification procedure, which is a state-selective microwave transition to have really pure circular Rydberg state in 51 circular level, which is the starting level for the experiment. So it's tricky, but under very good control now. Yeah? Yes. How to prepare entanglement? Indeed, so you start, the entanglement arises from this expression of the Rabi oscillation. So you prepare the E state, you put it in the cavity, let it evolve, and if you adjust the interaction time so that you perform not a full rotation, but a pi over 2 pulse, you have a linear superposition of these two states with equal weight, and this is entangled. So entanglement shows up like this. Maybe I missed the question. This entangled state, you mean? So experimentally, you prepare it by time evolution. So as you control here the interaction time, if you stop the interaction there, you are just halfway between E0 and G1, and you are halfway in a quantum way, which means that you are prepared the quantum superposition of E1 plus G1, and this is entangled. Okay? So no other questions? Okay, thank you.
Okay, so let's thank Michel again. So we restart in half an hour at 11:10. How many years did it take you to